Something really valuable about actually attending and being here in person is having the opportunity to actually ask the speakers while they're there, go up to the microphone, ask a question that you have, or meet them after the talk, chat them up in the hall. There's just a lot of opportunities if something isn't really clear to you to kind of just get in there and get a much clearer answer if you need one.
This is my first time attending CppCon in person, and I hope you are equally excited as I am to talk about security beyond memory safety. Now, I will first talk a bit about my perspective on memory safety, because it will be slightly different than what you've heard, for example, in Herb's keynote before. Then I will introduce myself and talk actually a little bit about security as a whole, because for the rest of this presentation, we actually want to come up with a secure design. So what actually means secure design? We need a way to actually discuss, argue whether something is secure or not. And after we have established this baseline, we can finally talk about how we can use modern C++ to avoid vulnerabilities by design. So let's start by talking a bit about memory safety. There's basically no discussion about C++ at the moment that doesn't talk at least a little bit about memory safety, right? And if you Google for C++, and especially the experiences that people have, especially new joiners to the language, you get descriptions that kind of working with C++ is like 50 shades of shooting yourself in the foot with a railgun. And while this may be due to inexperience, but how do new joiners get experience first, right? Maybe a lot of outdated tutorials and so on. A large part of it is attributed to memory safety, or the lack thereof, I would say, right? Because it's very hard to get into the language if you're only used to very high level, high abstraction languages that take care of everything for you. Or if you have never even written any programming language before. But it's not just the new joiners, it's also the people that have been there for quite a long time, right? You may have seen this press release by the White House from February this year, future software should be memory safe. Because those are kind of the users, or the people that get the products built in C++, right? And they are also caring about memory safety because, well, lots of bugs are attributed to that. But more important is the sentence below, address the root cause of many of the worst cyber attacks. And this is what I'm interested in much more. So let's look at what attacks are out there, right? This is the common weakness enumeration, top 25. I don't want you to read the list at all. I want you to focus on the title, because it says stubborn weaknesses. And they define stubborn weaknesses here as 15 weaknesses that have been present in every top 25 vulnerability list of the past 5 years. And then they analyze this list and they say, out of these 15, 5 are attributed to memory unsafety. So 1/3, right? And that's a substantial amount, I would say. And this is not just of academic structure or anything. If we just look, there was a nice article here. There's a zero-click Windows TCP/IP RCE that impacts all systems. Okay, there was an integer underflow in the IPv6 stack of Windows that caused a buffer overflow and enabled arbitrary code execution. So an attacker could just send a few IPv6 packets to your machine and take full control due to memory unsafety, right? And this is super recent, August 14th. Okay, so let's just use Rust and everything is fine, right? No, kind of. The problem is we cannot just use Rust, even if we wanted to use Rust now for everything. If you're working in embedded, the compilers are not there for all the platforms. If you have a code base that is huge, millions of lines, you are not going to convert this to Rust. The cost is just way too high. And then there's training people and so on. So a lot of arguments. I'm not going to dive too deep into this. But if we look now inside of C++, we also know that there is a lot of effort spent, and not just recently, right? We have the C++ core guidelines, and we have them for a very long time. They are focused on safety. We have then with C++11 stuff like smart pointers and so on. We got the standard ranges that help us make less mistakes, avoid these issues. And now erroneous behavior with C++26, which is going to be a great improvement here. And even around the C++ ecosystem with like CppCon, Carbon, Circle compiler, and so on, we have a lot of activities that want to address memory safety. So for the rest of this presentation, let's approach this burning topic of memory safety as if it was solved, or as if we at least don't have to care about it. There are smart people working on this, and they will hopefully find a solution. But the solution is not there yet. And we will still need to think about how we can work with the code that is written now, that has been written in the past, and that will be written in the future, to actually come to security beyond memory safety. Because even if we would now fix all of the memory safety issues, our software would still not be secure, right? You can take this from the numbers. 1/3 of the issues were memory safety related, but there is much, much more. Just to illustrate, there was this famous Jeep hack in 2015, where hackers were able to remotely take over several Jeep vehicles and completely engage or completely disable the brakes, for example, remotely, without any interaction. And it resulted in Chrysler having to recall 1.4 million vehicles. Imagine the cost. And there are also some other nice stories like this here, how I hacked my car, a blog post by GreenLuigi1. They wanted to install custom firmware on their infotainment system of their Hyundai, did some reverse engineering, found out that the updates are signed. So, well, they don't have the private key, they cannot sign, right? So they reverse engineered further, found the public key for the verification, Googled the public key, and the first match was an OpenSSL tutorial. So the key was taken literally, copy-paste out of a tutorial, where of course the private key was also written, and well, all leads to doom, right? So a really nice example, and this is exactly what motivates me. So hi, I'm Max Hoffmann, I'm from Germany, and unlike I guess many of you, I have not studied computer science at all. I have studied cybersecurity from the beginning at one of the leading places to do so, the Ruhr University Bochum. And even did my PhD there in association with the Max Planck Institute. And I'm still affiliated as an external lecturer there, teaching the next generations about security. Outside of that, I'm working as a security manager at ETAS, that's a subsidiary of Bosch, where we are writing software for the automotive industry. And I'm the security manager for all of our onboard core security products. So I'm handling everything from setting up processes, doing security reviews of designs, architectures, and code, but also handling vulnerabilities and so on. Just as a disclaimer, I'm not sent here by my employer, so the views I express are my own, not necessarily the ones by ETAS. Okay, let's talk a bit about security now. Because if I would do a poll, I would guess and ask you about like what is the relation between bugs and vulnerabilities. I guess the picture that we could paint is something like this. At least this is what I've seen a lot. And it's horribly wrong. Because let's look at a simple, real picture that shows you that vulnerabilities are actually like overlapping, but not a subset of bugs. So this is a real picture from the University of Bielefeld in Germany. And you can see this system is bug-free. Yeah? The barrier is raising, lowering exactly as specified. You cannot make it raise without an ID card. Everything is fine, but it's clearly vulnerable, right? And the reason is that, well, they are not overlapping. They are overlapping, but they are not one integrated into the other. Because bugs are about a violation of the intended behavior. A violation of the specification, and the specification describes what we intend. But security is not about what is intended, it's about what is possible. And we can clearly see the mismatch here. And well, the university saw that too, and patched the vulnerability by putting these stone pillars on there. But well, it took them apparently quite some time. So how did they even get into this situation first, right? That they had this insecure barrier installation. And we don't know, right? But one way we could say is that they had an incorrect attacker model. Because arguing about security is mostly meaningless without a proper one. Look at this. Like, raise of hands, is this secure? Is this insecure? Got to. You cannot raise your hand here. You don't know against whom. If this is a gate that shall keep out animals, I guess this is secure, even with a zip tie. But if your attacker model includes humans, or let's say the lock-picking lawyer is approaching this, the lock would open out of respect by itself, right? So then it would not be secure at all. So this is the main problem, right? We need to have a clearly defined attacker model first to argue about security. But it's really not easy to come to that point. Here's a nice XKCD comic to illustrate that. So crypto nerd's imagination, right? His laptop is encrypted. Let's build $1 million cluster to crack it. No good. It's 4K bit RSA. Blast, our evil plan is foiled. So your attacker model is like, I have a mathematician that wants to break my cipher. But the more realistic view would be, his laptop is encrypted. To drug him, hit him with his $5 wrench until he tells us the password. The very definition of a brute force attack. So it's hard to come up with an attacker model that actually captures everything. And I think the reason for this is a simple truth. Security is inherently complex. It's not something we can just discuss away. It is complex. And a single mistake can be devastating. But maybe we can counteract this a bit by focusing on solutions for this to make our software more secure, that are simple, that reduce the likelihood or the risk of making these mistakes in the first place. And one way to do this is with the super old wisdom, right, or design principle, to make the right thing easy and the wrong thing hard to do. But turns out, historically, in C and C++, the right thing and the wrong thing are equally simple or hard. Sometimes the wrong thing is even simpler, which is why so many people make these mistakes in the first place, right? And this partly comes down to, if you look now on the C side, that the entire philosophy around C is kind of trust the developer. But if we trust the developer not to make mistakes, we are not reducing the likelihood of the developer making mistakes, right? It's not getting us anywhere. But in C++, we have the compiler, right? And the type system. And maybe we can use this, leverage this, to actually build something that supports us here into reducing the likelihood of mistakes. So let's now talk about how we can actually use modern C++ to avoid vulnerabilities by design. And if I'm talking about using C++ and we look at the whole software development lifecycle, then what I'm talking about is actually secure coding, right? Or it's in the area of secure coding. So where we cross the boundary between design and implementation, and we try our best to mitigate the stuff that you cannot really or only hardly already mitigate on an architectural level. Let's set some expectations here. My personal bias is from embedded security. So of course, my examples here will be embedded related, but please don't let this take you off if you are working in web design or something. My goals here are explicitly that I want to show you examples that guard against these accidental mistakes, reduce cognitive load in reviews, and provide inspirations for your use cases. So even if you maybe cannot take something one-to-one, and apply this to your use case, you will find something in there that you can take with you. At least that's my goal. I also have a few non-goals. So I don't want to show you production-ready code. I don't want to present this as the only solution. There will be other solutions definitely to come to a secure design. And I don't want to present this or security solutions in general as plug-and-play solutions. Because I think there aren't any that are general plug-and-play solutions when it comes to security. You always have to think about security, and security is everyone's responsibility. So not just your security manager or security professional, everyone has to work towards a secure product. All right, let's start with our first example, and it's going to be a lighter one. Let's say you are working with secrets. It can be keys, passwords, whatever, personal data that you have to protect. So naturally, our goal is to erase those secrets as soon as we don't need them anymore from memory. We could come up with a very simple example here. We have a password buffer of 10 characters. We have a get password function. It's memory safe, it will not overflow. And we try to authenticate with this password buffer. And now what do we want to do? We want to get rid of the password buffer. So instinctively, we are going to memset this to 0. Maybe raise your hand. Who was thinking about this now as the first intuition? A few, don't be shy. Yeah? It's not bad that this is wrong, because so many people have fallen into this trap. any of the like slightly not outdated compilers, so even the embedded ones, which are decades behind, will actually optimize this out at a like reasonable optimization level, because it's a dead right. The compiler can see that after you have tried to authenticate, you will not access the password buffer anymore as a read operation, so it can remove this. So we actually need something like a secure erase function that is not getting optimized away, and then we are fine. Because our code rarely looks like this, it's more often looking like this, right? Where we maybe have our password buffer somewhere up here, and then it gets passed around, and then it reaches this legacy code barrier, and suddenly it's just a character pointer. And there's, of course, like then also a variable name or a parameter name that's not so descriptive anymore, so the risk of not erasing something down here is quite high. So let's now design a very simple class that helps us to get around this. So since we are working with sensitive data, let's call this class sensitive. And it gets storage for one object here of type T. We have our default constructor, and we have our secure erase function, which we will look at in a second. And then when we destroy this class, we will just call secure erase to clean it up. And now, by design, kind of, we can be sure that it's always erased. But let's go further. We also want to remove copy operations. This is not necessary for security per se, because we can be sure that it's cleaned up, but it's sensitive data. I want to have it in as few places as possible. Then I'm creating move operations, and I'm doing this very, very consciously, because like semantically, a move is taking something, putting it somewhere else, right? The origin is gone, but we know in practice it's not gone, right? In practice, a move is a selective copy, we could say. And let's say this T is our standard array of something, then it will copy over. So we have to be careful to also, during moves, actually erase our memory, because if you have something like a static object that you move in and out of, you would never erase otherwise. And then finally, now we have secure storage, but no way to access this, right? And we could just have a getter that gets us like a reference to the internal object or something. But it's quite easy to make accidental copies this way, right? So maybe we do something like this, that we say we have a with sensitive content function that you can pass any other function or lambda into, and then it invokes that function on the content. Now, of course, you can still somehow screw this up and create copies and whatsoever. But by forcing here with this using statement that the parameter is taken by reference, at least I can avoid that there's a copy in the parameter. So where does this take us? Well, we will no longer have this situation from above, right? That we reach legacy code or badly written code just like that. We will either have in the type signature that this data is sensitive. And this will like show up for a developer. This buffer is somewhat secret, better be careful, right? Or you will access the data with sensitive content, and then this should scream, review me, during a code review. This makes people aware. It's kind of like the unsafe block in Rust, right? It's not bad to use unsafe if you use it only where necessary, but it makes the reviewer actually be like attentive and really, really thoroughly review this. And this is exactly what I want to achieve with this. Now there's one thing missing, the secure erase function, right? That I gracefully walked around so far. Let's look what we have at our disposal, right? We have memset, okay, not applicable, it gets optimized away, but we have memset explicit since C23, and we have memset S since C11, so also available in the C++ libraries, of course, except if they aren't. And they aren't. They are still largely unsupported. I tested this on Compiler Explorer, and, well, they didn't work, at least for GCC and Clang. But they were explicitly made for this use case of not being optimizable away by the compiler. And it turns out even if we now do some shenanigans with like volatile pointers or with compiler barriers, this is still not guaranteed to work. In fact, this is still a topic of active research in the security community. This is a paper from 2024 about high assurance zeroization, that you really solve this issue of getting this stuff erased if you really want to. So yeah, not going deeper into this rabbit hole, but if we go back to the problem we wanted to solve, I would say our class really helped us here, right? We either have it encoded in the type, that this is something sensitive and we need to be careful, Or we actually, if we need to access it like raw, we do it in a way that is very expressive and makes people attentive. So, tutorial completed. Yeah, this is the first use case, and I think you now kind of see where I'm going with this, right? We are going to design quite simple helpers that then avoid mistakes by design. So now let's get to the real thing. And we are going to build a product together. And our product is the friendly billboard. So let's say CppCon contracted us and set up our friendly billboard outside of the venue. And then we deliver them with a small chip that has our friendly billboard firmware embedded, and it's communicating to the actual billboard outside through Wi-Fi. And then some volunteers here are going to write the message receiver application that will then communicate through shared memory with our firmware. Okay? And we chose to, let's say, use a website. So you can send nice messages like C++ rocks, and the message receiver application will take this, wrap it into a command for our firmware, send it through the shared memory. Then our firmware will make sure that it's actually a friendly message. We'll update some internal statistics and send it to the billboard. And so we can greet now other attendants to the conference with nice messages. And if someone is angry, maybe didn't get a ticket anymore, and they want to say something mean, well, the receiver application would still hand this over to our firmware, which would do the friendliness check, would say, oh, this is not friendly, would update the statistics, but exit from there. So far, so good. This is the product we are now going to build and secure. And if we abstract a little, you find this style of application actually a lot, right? That you have some other application that is not written by you, that is communicating through some shared memory, or something like shared memory with your own software. You find this, for example, in drivers, operating systems. This is like a nice demo of generic IPC, right? And if you are working in the security domain, so with trusted execution environments, for example, you will typically work in this style to communicate with them. So let's now come up with a program that would just implement our friendly billboard driver, functionally correct. So we start with a show message command. It just has a string view of the message to show and an output pointer status to report back to the application whether we accepted or rejected the application. And then in our firmware, we are going to deserialize this show message command, and then we are handing the two parameters off to our process message command function. It takes the string view, takes a reference now for the status, and the first thing we are going to do is to check, is it friendly? And update the status with then acceptance or reject. We update our statistics, and if we accept it, we are going to show our message on the billboard. Now, I hope you are at this point convinced, or at least kind of happy with this code in a sense of it's functionally correct. It will show the messages, it will block unfriendly messages. Nice. So now we get the requirement to make this secure, which is a bad requirement because it's not testable at all. But okay, we want to make it secure. So what could be our attacker model here? Well, the entire right side is written by us. So let's say here we want to focus on, here we have control, but the left side is written by the customer, by someone else. So there we don't have control. Of course, if it's written by our CppCon volunteers, it's gonna be secure, but we will sell this to others too, right? And we don't know what they do. So let's assume that our attacker has taken over this site completely. This is a worst case attacker, right? But it's fine for our software to assume that, because from our point of view where we have control, this is the worst that can happen. And the attacker goal is that they want to display an unfriendly message on the billboard. Now, this could look like this, okay? The attacker has, through some exploit, taken over through the web interface, the receiver application, and now they can send any update text command to the shared memory. And since it's attacker-controlled code, all memory safety, all synchronization primitives, everything that is normally used is gone, okay? Because they can just inject arbitrary assembly. They don't have to conform to any rules. They don't have to use anything memory safe. All bets are off on the left side, and we still have to be secure. So if this is what we are starting with, I want you to take a moment and think about how many vulnerabilities you think are in there. So let's see if you were correct. We are now going to fix them like in an evolutionary style one by one. And the first thing I want to look at is input validation. This is actually also one of these like CWE classes that are frequently reoccurring, right? That this is not done properly. So everything that is coming from our potential attacker or that is outside of our trust boundary, we need to see as untrusted. And we need to handle it with care. We need to validate that everything is fine, okay? So let's say we have some input T, and this is untrusted, right? We make this clear through documentation. Now we have two ways to handle this. The first one is through verification or validation. Depends on what you are doing here, but you are going to check this value. You are going to do something like, if input is larger than my maximum allowed value, I'm going to raise some kind of error. And the other way we can do this is through sanitization, which we are now all familiar since the COVID pandemic, right? We want to take something and cut off everything that we don't want. You know this maybe from like HTML, HTTP escaping and so on, where you make sure that you transform the input to something that is now in your expected like alphabet boundaries, whatever. And you can now say, okay, but we did this. This is input validation, what we do. We check whether our message is friendly. And you're right. But first, the raw value is always accessible. It is possible to forget this check, maybe not in such a simple application, but in a larger one, definitely. And no one would notice because you can access the raw value all the time. And from a developer point of view, how do I even know that I have to validate here? How do I know that it hasn't already been checked whether it's a friendly message or not? Right? So let's come up now with our first class that helps us here. And since we are working with untrusted values, let's call it right that. Untrusted of some type T. I no longer need documentation to write this is untrusted. It's in the type, right? And then we can validate or verify maybe this way, that we say we have a verify function, and we pass it a function, a lambda, whatever, that returns a Boolean, whether we want to accept it. And then it returns me an optional of the internal type. So if it's fine, we get like some of that internal type, or we get the null option. And we can also sanitize this way by basically just providing a function that mutates the internal value. So kind of like we had with this sensitive thing, where we provided a function that then works with the internal value. We do the same thing here, but we add more logic to this. And we can quite easily write some class like this, right? So untrusted T has storage for some value here. We had our constructors, copy move operations, and then we have our sanitize function that takes this sanitizer and just calls it. Easy as that. And we can do the same with verify. Here it's maybe a little more complicated, but it's all just calling the predicate, checking the result, returning the optional or the null. And even if you are not working with C++17, where standard optional was, I think, introduced, you can write an optional type that fulfills this yourself, even in C++11, right? So you can take this back in time to also older code and apply this there. Now let's update our code with this. So we are now looking at this process message command function. Previously, it just took the string view of the message. Now it's getting an untrusted string view. And this forces us now to actually verify the message here with our isFriendly function. Not much change to before, right? But now to update our status, we check whether we have a value in there. Then we update our statistics as before, and we check our status as before, and then we show on billboard the data that is in the optional. So nice. Now the raw value is never accessible. Nobody can forget to sanitize or verify here, or at least we force them to do it at a later point. Right? So it's impossible to forget, and it's absolutely clear whether we still need some validation to perform some validation or not. And of course, you can enrich this class to maybe have some compile time string that gives you a reason what you still need to verify or something, right? Be creative with this. Support the developer in not making mistakes. Now you can say, okay, I get it, but we already had some kind of input validation, right? So why the effort? This is hard to reason to invest the money. But my point is, we are not done with input validation. There are more inputs here that we did not validate and that will actually cause vulnerabilities here. Let's look again at our message command structure. It contains the string view and this output pointer, right? And in a normal usage, we would get our string view, which has a size and the pointer to the data, and it would point to the string message C++ rocks also in shared memory. But nothing stops an attacker that has full control to just send us a manipulated string view. And it's no longer pointing to shared memory, it's pointing somewhere into our own firmware. Maybe where the Wi-Fi password for the billboard is, so that it greets everyone directly with the exploit, right? And this is perfectly possible, and this is oftentimes done as an exploit, especially in embedded systems, because this is also an input, of course, right? It's not the string view as a whole, it's also the parts it's made of. And to better illustrate this, I'm going to split up the string view now for the rest of the presentation into its character buffer and into its size. This is not necessary for security, but it illustrates the point better. And now I'm going to do some extra step. I'm going to auto-generate a second version of this struct. And maybe we can use reflection when it's ready, right? But you can easily do this with some text processing at the moment. And what I'm going to do is I'm creating one header of the API, and I'm giving this to our customer to implement the functionality they need. But I'm keeping an untrusted version of the same header internally, and I'm only going to use that. I'm going to write a very simple like git diff grep to make sure that I'm only using this and not the other. And I'm running this in my CI every time. And now I can update the code that is doing the initial parsing that was initially just like memcopy. Okay? And now we are actually going to do a little more. We are going to deserialize, so memcopy first the untrusted version of the struct. And since they are layout compatible, I have to ensure this, of course. This is not an issue. And now I'm forced to actually do my input validation for the message, for the size of the message, and also for the output pointer, which, by the way, we didn't check at all before. Right? And I can just check that, for example, my message is in shared memory, the output pointer must also be in shared memory, and my length, I don't care, I just truncate it to the max length that is allowed. And then I can continue. If both are valid, right, I'm rewrapping this now into a string view so that I can pass it off, or even an untrusted string view, so I can pass it off to my process message command as before. And if something went wrong and at least my status was fine, I can just say, okay, I rejected this point already. So this is where we are right now. And we actually took care now of all input validation issues, at least those that I've seen. Now update your estimate, right? I asked you before, how many vulnerabilities do you think are in this code? So far, we would have, like, let's say at least 3. Update your estimate. So let's see how many are left. Well, we will focus now on the process message command again. What we are doing essentially is we are verifying that the message is friendly, and we already know that the pointer and size is fine, so nothing can go wrong there, right? Then we are updating the status, and then we are updating our statistics with the status and showing the message on the billboard if the status says accepted. And maybe just by the way I pronounced this now, you already saw it. So the attacker wants to put C++ sucks on the billboard and is sending this over. And we will do this friendly check and will reject this, right? So we would say, no, this is not fine. It's an unfriendly message. And we will update our statistics. And exactly at this point in time, the attacker will come in and just memcopy over into the shared memory, which is perfectly fine, right? It's a shared resource. And as I said, like, the attacker does not have to obey any like synchronization primitives or anything we would have put in place. Unless it's hardware protected, of course, right? Then maybe we can do something here. So now what's going to happen is, well, assuming that our update statistics function is large enough so that the status is not kept in memory or something, in registers, it has to refetches from the shared memory. It sees, yeah, it was accepted. It wasn't, we just faked it to be, and it will show this unfriendly message on the main billboard. So this is quite a nasty vulnerability, right? Because it involves time. And reasoning about time is really, really hard when your code becomes larger. I mean, maybe you can do a show of hands, like, who did not see this vulnerability before? It's the majority. Maybe not the large majority, but it was the majority. So it's hard to see even in such a small code, right? Now, how can we prevent this? Well, the problem, if we condense it down, was that we were reading from an untrusted source, kind of, and we were doing our control flow based on this. if I pronounce it like this, like we were trusting an untrusted source to make a control flow decision, doesn't sound too great, right? And this only happened because the status variable, it was intended as a pure output parameter. But this somehow got lost, right, through the different layers of code. So let's bring this notion back through the type system. We are going to write a very simple write-only class. So we have storage for a t pointer. We're going to be able to create it from the pointer, and the only operation we kind of expose is the assignment operator. And then we just assign it. We can no longer read it. I mean, for the opposite direction, we have something in the language. It's called const, right? But for write only, nothing like this exists. And we can now easily update our example again. So instead of just getting a status reference here, we are getting a write only status. Now again, everyone that reads it, it's crystal clear without any additional documentation what we are intending here, right? We want this to be a pure output parameter. And then all we do is we have to keep our verification result that we are doing. We have to keep this in a local variable. And maybe we should have done this in the first place. Or maybe we should have had this as a return value, right? But, well, this is like example code. And I guess in a sufficiently complex example, you will find such a construction where this is actually crucial. Now, we at some point write to our actual output parameter, the status, our local status. We update the statistics with the local status. And if our local status was accepted, we will show this on the billboard. Now, you could say, wait a minute, if we do this exploit and override, like on the old version, override the status, we would actually, when we show on billboard, we would like dereference or take the value of a null option, right? Because it was rejected before, and our untrusted type will return an optional, and since it failed, we got the null option. And I tried this. I did a debug build. It crashed. I did a release build, and it printed C++ sucks. Yeah? So even though it was technically a null option, and we used just the star operator, the dereferencing, so not the dot value, which is fine because we checked has value before, right? So it's not even something where we made a major mistake. If we do this in a release build and an attacker actually fools with the guarantees that we would expect from our intended code, all bets are off again. So that's the first vulnerability. And now there's actually one vulnerability left. And it's again going to involve time. And it's again in our process message command. And maybe you have now already guessed it. So there's only one thing left, right, that we didn't explicitly talk about. And this is the string content itself. So C++ rocks, right? Because what we have at the moment is our string view. It's in our memory. It's validated. It's fine. We do this friendly check, but we do it on the string content that is still in shared memory. Well, we accept, it's fine. We update our statistics, and now at the same point in time, our attacker comes in and changes it to the evil message. This is going to work perfectly fine, right? It's the same problem as before. So when we send it to the billboard, we will actually now read back from the shared memory and will print out C++ sucks. And this is now maybe an even nastier form, or maybe even a more generalized form, depending on how you look at this, of the vulnerability that we had before. And it's a so-called time of check versus time of use vulnerability, or TOC2. And the name is quite descriptive, right? We had a time where we did our check, but the data changed to the point where we used it. And where do you know this from? Race conditions. But the point is, this is kind of like, this is a weaponized race condition, right? And unlike a race condition, which typically can show up during normal use, right? If your network latency suddenly spikes up, you will get your hidden race condition or something. A time of check, time of use vulnerability typically does not show up never during normal use, only if someone maliciously interferes. Like, of course, exceptions apply, right? It's again an overlap of the two classes, but this makes them so hard to spot because it's in no way of testing, let's say generalized testing, you will be able to spot those. You have to be really like trained. Your awareness has to be high. The awareness in every developer has to be high that these things exist. whenever you are working with a shared resource that is shared with at least one untrusted party. And always then you have to think about time of check, time of use issues. Now, how can we solve this? Well, maybe we could come up with another nice helper class, but yeah, unfortunately, there's not enough time to dive into this anymore. So let's think about how we can maybe hotfix this and delay this for another presentation. So the point is, the string itself, the string content, remained in the shared memory. So let's just pull it out. We are no longer going to use a string view, we are just going to use a string. It's owning the content, right? Of course, now we need heap allocation and so on, right? But by just pulling it now in here into the memory of our firmware, it's no longer in the shared memory, the attacker can do all the override shenanigans they want, and we are still secure, right? So if we go back to the example now, but with our fix, with our patch, we would first copy this into our internal string. We do the friendly check on that string. It's fine. We accept. We update our statistics. The attacker does the override, but we don't care at all because this memory is no longer used by us. So another way of looking at how we can actually mitigate time of check, time of use vulnerabilities is by reading the data only once. No matter what data it is. Because either the attacker corrupted it before, but then it's like, yeah, they corrupted before, it's fine, right? We read it, we validate it, we reject it. The attacker manipulates in the middle. Okay, then we have partially manipulated data, which is the same as if they just partially manipulated it before. We still have to do our verification, we will reject it. Or they manipulate it afterwards, but we are not going to read it anymore. We only read it once, right? So this read or access the data only once is quite a reliable thing to fix these time of check, time of use issues. But this gets quite hard if you think about your shared resource maybe as files on a file system. And you do some checking, and you have to keep the file handle open at all times so that it doesn't get accessed again and stuff like this, right? So time of check, time of use, it's not just about raw memory or buffers, file system, some shared network queues, and so on, right? Be creative again. Think like the attacker. How would you exploit this to get to the point? And this is where we now end up with. Yeah? This is our full secure, I would say. Yeah? At least I didn't see any other vulnerability in here given the environment that we now assumed. This is our fully secure, friendly billboard driver that we generated here together. Let's just walk through it one final time to see where we ended up with, right? We are deserializing our untrusted version of the show message command. It has all members wrapped in untrusted, so we cannot forget any validation. We cannot access them by accident. So we do our input validation now, and we can be sure that the data is fine afterwards, and only then we can access it. Now, after we did our checking, we are rewrapping this, our string, in another untrusted string, this time an owned one, to get around the time of check, time of use issue. And we are wrapping our output parameter, the status pointer, into a write-only wrapper, so that it's crystal clear this is only output and nobody can, by accident, use it as an input. And then we hand this off to our process message command, which will do the remaining input validation. It's all fine. We now have our final string we want to show. We do our friendliness check evaluation, but we do it in local memory because we are forced to by the write-only class. We update our statistics and we show only the most friendliest of friendly messages on the billboard, right? So we are happy, and this guy definitely not, right? They now have to go off because we ended up with something that is actually secure by design. And we made it really, really hard for someone to make a mistake that, again, invalidates our security here. And how did we get there? Well, we thought about what is possible, not just what is intended. And we came up with a reasonable attacker model in the scope of what is possible. And we assumed the worst case here, right? But only assuming the worst case here, in this example, brought us to a solution where we now could actually confidently say, hey, we actually looked at everything we found, covered everything. Human error is always possible, but at least we did our best. And we did this in the end, technically, by using C++ to make the right thing easy and the wrong thing hard to do. So by this, we finally achieved security beyond memory safety, right? And as I said in the beginning, like, this was now embedded focused. But you see the thinking that went into this, right? The way of how we designed our helper classes, and they are super thin wrappers, right? None of them have additional storage over what we anyway would have invested. So proper zero-cost abstractions. All of that, what we invested in these wrappers, was there to prevent mistakes and to get to expressive types. Because what I see a lot is all of this, what we do, expressed through documentation. And the worst case of documentation is that it is not even at the code, but somewhere external. Because we all know the situation, right? There's time pressure and so on. I mean, we all read the documentation, hopefully, when we start using something, but at some point we get so used to it, we no longer look at it. But maybe there was this small detail that we just missed so far, or that would be now important. So documentation, sure, it's super helpful, but not for security. For security, I want to put as much as I can into things that are enforced automatically, so that I can guard against those accidental mistakes. Now, you can always come up with other alternatives. As I said, this is not the only solution. For example, we talked about this untrusted type, but maybe you are working with an application that is doing like tons of input processing and only very little core processing. Then maybe you don't use an untrusted type, you use a trusted type. And then in your inner API, you only use the trusted type, so you are sure, again, by design, that you somehow did your validations before. Again, be creative, come up with solutions that like really support your security use case against your attacker. And in case you're curious, I uploaded the entire code that you saw here. It compiles, it builds, it runs, it prints, and it has the exploits in there that we talked. I uploaded this to GitHub in its like non-production code quality. But if this is useful to you, we can maybe collaborate on this becoming an actual useful like secure coding library. And that's it. Thanks to the nice creators of these amazing icons that you saw in the presentation. And thanks to all of you for attending. So I guess we should have like 10 minutes for a question.
If anyone has any questions, please let me know. I'll be there with the mic.
Great talk. I enjoyed the designs a lot. I have a question. Is there potentially another vulnerability if we check the pointer separately and the length separately? So what if the pointer points to the end of the shared buffer?
So the question was, what if the pointer points to the end of the shared buffer? We are checking pointer and length separately, right? We are not checking how they work in combination. Yeah, okay, now it really depends on your memory layout, right? But if they overlap, right, this could be definitely a problem. Yeah. Good catch. Any other questions?
Hi, thanks for the talk. I'm curious, how is it even possible for those attackers to interleave our code execution and change the shared memory right at the point of validation, post-validation, and how can we protect ourselves specifically from these kind of malicious race conditions?
Mm-hmm. Yeah, that's an interesting question, right? How can we prevent that the attacker can actually do this modification at the right point in time? I'm going to start with that. And that's basically, again, by pulling it all into our own memory. That's the simplest solution. It doesn't mean it's the most optimal. It costs performance, right? And we don't have to pull everything in. Sometimes we are just operating on some data, and if the data is wrong, well, we are outputting something that is also wrong. Like, let's think about sensor readings, which are sometimes wrong. We don't care if this is manipulated or not in some applications, right? So there we wouldn't have to copy. But the general advice would be, if you need to work on this data, copy it in and do everything on your local copy. Now, your first part of the question was, how would someone actually exploit this, right? How can they actually get to this point? And the thing is, you should never underestimate how creative attackers get when it comes to getting to what they want. We have to think about the software as a whole. We have to plug every hole. We need to be 100% secure, which, by the way, is kind of a thing of impossibility. But they only need a single weakness, right? A single vulnerability to go through. And I, as someone who has really spent a lot of time in security, would definitely go to these interfaces that are processing data a lot and just try to change something after I've set off the call. And it's not hard to automate this simple for loop that does this 1,000 times, waiting a few more milliseconds, right? Tailor this to your application, but it's definitely possible, right? If you want to hear more about like how creative these people get, make sure to come to my open content session this evening, where I'm going to talk about what can go wrong if your random numbers are not as random as you would like. But it's going to be much more entertaining and less technical.
Hello. Hi, thanks for the talk. I know you kind of ran out of time on this, but do you have any thoughts, like how could you suggest a way from a developer picking string view over string when string is the right thing in that?
Okay, yeah, so when should we pick, as a developer, string over string view in such contexts, right? If we rephrase this slightly, when should we use a type that owns its memory over a reference type in some shape or form? And it all depends, going back to the big picture, on our attacker model. This is, if you remember, I showed this picture of the software design lifecycle, right? Where the attacker model is basically the very first thing you have to think about. And the attacker model is also something that needs to be understood by everyone, including management. I had this several times that I went into discussions with people from management who were talking about this. This is the attacker model. Yeah. Okay, are you aware that this attack would work? Wait, right? And this was the point where it made click. So really everyone has to understand the attacker model, and then you can come up with discussions about this, right? Where is this memory pointing to? Is it a reference type? Where does it point? Where is the actual data? Do we need to copy this over? So this is the line of thought that should happen.
But this is like a cultural process.
Yes, it's a cultural thing. It's an awareness thing.
Thank you.
Thanks for the talk. Yeah, so looking at that diagram with the shared memory, the model itself sounded very risky to have shared memory in place. So generally, my idea when I was working in embedded systems is that for same applications running on one system, if they have to interact, shared memory is one of the possible solutions. But in this case, if you want to update a message on the billboard, it would be two different systems, right? That's what I had in mind. So it wouldn't be shared memory in that case. So what kind of real-world examples this would have? And I have like a follow-up question. If it was not shared memory and it was over network, what kind of security concerns, like top 2-3 security concerns we would have if it's not shared memory, and instead if it's socket programming or something like that?
Yeah. So for the first question, what if we do not use shared memory at all, right? So we are still in the kind of embedded context, or let's say we have a system context, but we are not using shared memory. And this is what you typically find when you are using an operating system that has different processes running on there, and you are not necessarily communicating through shared memory, but through shared files. Okay, now you could say this is also some form of shared memory, right? It's maybe not shared RAM, but shared memory. And this is kind of what this comes down to. It's always about shared resources. And it does not necessarily even have to be shared storage resource, so memory or file or whatever. It can also be a shared accelerator for something. Anything that you share with an untrusted entity, you have to kind of come up with this design. There's a really nice talk on the security of the Xbox One, how they designed this from scratch, the SOC that they use to actually work in an environment where everything external to the SOC is untrusted. If they write something to the hardware, to the hard drive, read it back, they assume that it could have changed. And they came up with a security design that encompasses all of that. So I highly recommend you to check out this talk to get a better understanding of how this would work. Now, the second question was about, now we are leaving the embedded context a little at least. We have networked communication and so on. What do we need to worry about in this context, right? So time of check, time of use is not that applicable, I would say, because you have less shared resources with the access in the way that you would do on one system, right? But you get other issues there. You have, especially when you do web communication, all of your regular authentication problems, right? All of the authentication bypasses. You are tending to get to an architecture that has many more communicating parts. And that puts the complexity just somewhere different. So now, again, the advice would be, come up with an attacker model, and if your services are communicating over the internet, you might have a different attacker model for every of your different services, right? And then you have to secure each and every one of your services against your hypothetical attacker. And then this is the best bet you can do, I would say.
Is this notion of an attacker model formalized enough to the point where we can prove that there are no vulnerabilities left in this code?
That's a very good question. So is it formalized, the attacker model, is it formalized or formalizable maybe in some technology that we use so that we can prove the absence of vulnerabilities? Yes and no. So there are, especially now in the academic context, there are formal verification methods or even compilers that can actually like take some input. It's no longer like C, but yeah, lots of annotations and so on. And then it can, for example, prove the absence of timing leakage. So that different branches through your code have different execution times that depend on a secret value. Because through such a timing side channel attack, it's actually possible by observing many different invocations of your function to extract secrets just through the timing. And this works even through the internet traffic with nanosecond fluctuations. So it's really that powerful. But in general, so just here's my, don't know, high-level language model description of my attacker model. Tell me if I'm secure. No, there's no such thing.
Right, I was going to ask you, how do you prevent a large language model from repeatedly querying your isFriendly function to learn about the algorithm that was used to return true or false, and then use that understanding of your isFriendly algorithm to pass in a very nasty string?
Mm-hmm. So in this example, I clearly don't. Yeah. But what you can do, if this is kind of what you know, it is possible in your attacker model, right? So you should kind of consider that. And you can say, hey, are we using maybe a whitelist? And only words from the whitelist are allowed. This is your most strict form of restricting inputs, right? This whitelist approach. And then the language model can do whatever it wants. It will not be able to do any sentence you cannot build from the whitelist. And then maybe you can use your own language model to check, can I generate a mean sentence from the whitelist, right? To verify that it's a good one. What you could also do is, of course, yeah, I see I cannot prevent this problem, and I acknowledge this. How can I mitigate this attack somehow, that the attacker, let's say they would need millions of queries, that they cannot do this. And maybe I implement that on my firmware, I wait 10 seconds between each isFriendly invocation. Our friendly billboard out there should not flash new messages at the viewers, right? So maybe this is a reasonable way, and then the millions of queries would be out of question, right? So this would not be like a solution, a 100% fix for this specific vulnerability, but it would make it infeasible for the attacker. And this is something we typically strive for in security, because I can always invent a stronger attacker, right? I could say, okay, now my attacker is able to take the device apart, maybe to even like desolder the chip or remove the package and do needle wire probing on there. It's all possible, but how do I prevent this in software, right? At some point, I'm gonna lose. I just want, in my reasonable attacker model, make it so hard that it's infeasible for them. That's the goal.
Thank you.
Hi, thanks for the talk. I have two questions. So basically, I think this kind of attack can be maybe split by embedded or non-embedded system, because in embedded system, we have a trusted execution environment, which is TEE, and it already established this isolated memory. So do you think we still need to like use the copy memory trick to prevent this this attack? And the second question is, for the non-embedded system, actually, we still need to deal with large amount of data. So yeah, basically, it's similar to previous guys asking. So how do you think we can maybe not using the copy memory to prevent this kind of attack?
Okay. So let me start with the second. So how can we, when we are working in a non-embedded context with lots of data, how can we maybe prevent the copying around? It's expensive, right? It costs performance. So as I said, just copy everything is your simple solution that at least prevents these weaponized race conditions. And it does so reliably. But it is like sometimes like it's an oversized solution for what you try to do. Maybe you can, depending on your system design, put the data directly somewhere where you know it can be trusted, right? Maybe you don't have to move it around if you can instantiate it directly at this point. Maybe you will find some other means in the architecture that you use. I briefly mentioned some hardware support for locking down memory. If you have something like this, and you have this definitely also outside of embedded contexts, maybe your operating system can help you with this to lock down certain memory against manipulation. Use that, right? The amount of systems I've seen that have executable stack where they don't need it is alarming. Just disable stack execution and buffer overflow exploits get so much harder. But it's something we have to actively do, talking about defaults again, right? And most defaults are not security favored. So now I forgot the first part of your question, so can you repeat this?
Sorry, first question is for the embedded system, we have TEE, trusted execution.
Okay.
Yeah. It's already isolated, so do you think we still need to copy data to prevent this attack?
Yeah, so if you have a trusted execution environment, it's basically an elevated part of the processor, we could say, right? It is fenced off against the rest. So from the TEE point of view, the attacker model is the rest of the system, or at least some parts of it are malicious. So the TEE itself is the one that has to do the time of check, time of use prevention. And I have actually worked with some like a TEE internal like functionalities so that you design them in some larger TEE framework. And there also the guidelines were explicit, like take care of your memory, copy it in, be aware that it can be changed and so on. But if you do this properly, and then in addition to do proper separation of the different users of the TEE, then maybe you as the application developer can be more relaxed about it. But it depends, and you should think about it in the concrete context.
Thank you.
So,
yeah. I have a question. So here we are still assuming that the instructions responsible for the is validation part, those are still executed. As an attacker, am I allowed to assume that because of the creative space, I can, let's say, I somehow fluctuate the voltage and manage to not execute those cycles, those particular cycles responsible. So is there anything that we can?
Yeah, so what you are talking about here, if you are asking about can we as the attacker somehow skip the is-friendly check at all? In the scenario that we are talking about, where we have like a chip and we have a web interface and the attacker comes through the web interface through some exploit on the chip, I would cautiously say there is no way that the attacker can do this. Because what we are talking about would be a so-called fault injection attack. And typically for fault injection attacks, you need physical proximity. You need to somehow play with the supply voltage or with the clock. And then you can actually quite reliably make the processor do some mistake. Typically as the attacker, you don't even know what mistake, but you just repeat this a few thousand times and suddenly your debug port gets opened or your unfriendly message goes through because you can actually cause instructions to be skipped with this, yes. But yeah, physical proximity is required typically.
Thank you.
One of the things that was really obvious to me throughout that talk is that the idea of time is central to a lot of these vulnerabilities. Is there a way we can make that explicit in the type system, encode our ideas of time?
Yeah, so yes, time is very essential to these advanced vulnerability issues. To be fair, if you visit a secure coding training or something, those will likely not come up. At least I have not seen them come up that often. Because they are advanced, but they are still very real, right? So how can we put this in the type system maybe? Honestly, I don't know. But I've also not invested too much thought in this, I must say. Maybe we can. In Rust, we can use the type state pattern, for example, right? That we can encode the state an object is into its type, and we can prevent certain use cases based on the state of the object. I don't think this is easily expressible in C++, but that could maybe help us here. But it's definitely something we could think about. It's an interesting idea.
Thank you.
Thank you. All right. And I think that's it. Then thank you again.